Hello everyone, welcome back. This is the second lecture on designing IIR filter using bilinear transformation. In the first lecture we have discussed bilinear transformation design method. Let me just recall what we have done in the previous lecture. So what is the design method? So given a digital filter specification, okay, so basically we said that it's not possible to design digital filters directly the way we used to do it in FIR filter. There are few procedures we need to follow, right? So given a digital filter specification, what we need to do is we have to convert it to analog filter specification. Right? Okay, so how do we do analog filter specification given a digital filter specification? Using what? Transformation with frequency warping, right? Now once you get the analog filter specification, what I need to do is I have to get analog filter transfer function h of s. It's an analog filter, it's in S plane, okay, it's in Laplace domain. So but how do we get this analog filter transfer function? Using low pass prototype filter, right? Using low pass prototype filter, right? uh, if the thing is, if the given specification is for high pass or low pass or band reject, what is that I need to do? I need to get h of s analog filter transfer function using low pass prototype filter. Okay, now once we get the analog low pass filter transfer function, now I have to get the digital filter h offset, right? Fine. Now in order to convert from analog filter transfer function to digital filter transfer function, we use a transformation method called as bilinear transformation. We are using bilinear transformation. We have one more transformation called as impulse invariance transformation, but it's not there, right? It's not there in our syllabus, so we are not going to discuss it. So we are discussing bilinear transformation to convert from analog transfer function to digital transfer function. Okay, now if I'm trying to find a low pass filter, what I need to do is I have to use this low pass prototype filter to transform from low pass to low pass. If I want to design a high pass filter, use the low pass prototype filter and do the frequency transformation to get high pass, right? To get band pass filter, use the low pass prototype filter, use the transformation to get the band pass. If you want to find band stop filter, again use the low pass filter prototype low pass filter, use the transform function to get the band pass. And the equation for this transformation, frequency transformation, that is low pass to high pass, band pass and band stop, we have discussed in lecture 1. You go through that video. Okay, we shall take up a simple example to convert a prototype low pass filter to high pass and band pass. How do we do that? Okay, how do we use that frequency transformation to convert a low pass to high pass or low pass to band pass? Okay, so example, given a low pass prototype transfer function hp of s is equal to 1 divided by s plus 1. So determine each of the following analog filters. So first one, A, the high pass filter with a cutoff frequency of 40 radians per second. Next, B, the band pass filter with a center frequency of 100 radians per second and bandwidth of 20 radians per second. Okay, Okay, what is it he has given? He has given a prototype low pass filter. From this prototype low pass filter, what I need to do is I need to find analog filter for high pass with a cutoff frequency of 40 radians per second. Again, for the same prototype filter, I want to determine band pass filter transfer function with a center frequency of 100 radians per second and bandwidth is 20 radians per second. Okay, so we'll try to get this. So solution. So what is it I need? I need is high pass filter, right? Transfer function for analog high pass filter. Okay, how do we get this analog high pass filter using prototype filter? It is nothing but HP of S. In this HP of S, wherever S is there, I need to replace it by omega C by S, right? Where omega C is what? Cutoff frequency. This we have discussed, right, in the lecture 1. So in order to get high pass filter transfer function, in the prototype low pass filter transfer function, wherever S is there, you replace it by omega C by S, where omega C is the cutoff frequency. Okay, we'll do that. So what do we have? H high pass of S is equal to H prototype of S, where S is replaced by omega C by S, right? So H high pass of S is equal to what is HP of S? It is given, right, which is 1 divided by S plus 1, right? So S is equal to omega C is the cutoff frequency, and what is the cutoff frequency they have given? It is 40 radians per second, so it is 40 by S. Okay, so H high pass of S is equal to 1 divided by, so S has to be replaced by 40 by S plus 1. So this is equal to, if I take S by S, S goes to the numerator, and these two S I can take common and it goes to the numerator, so it is nothing but S plus 40. S divided by S plus 40. So therefore, high pass filter transfer function with the cutoff frequency of 40 is S divided by S plus 40. Okay. Now, so B, this is the solution for A, and solution for B. So what I need is band pass filter transfer function for the band pass filter, and it is given by prototype low pass filter. So in this transfer function, wherever S is there, I have to replace it by S square plus omega naught square divided by S into W, right? So where what is omega naught? Omega naught is what? Geometric center frequency, which is 100 radians per second. It is given, right? And what is W? W is the bandwidth, which is 20 radians per second. Okay, so H band pass of S is equal to HP of S, and what is HP of S? It is given 1 divided by S plus 1. So wherever S is there, I have to replace it by S square plus 100 divided by S into 20, right? So H band pass of S is equal to 1 divided by S square plus 100 divided by 20S plus 1. This is equal to 20S in the numerator. If I multiply 20S on the both side, this divided by, so I have S square plus 20S plus 100. So therefore H band pass of S is given by 20S divided by S square plus 20S plus 100. This is 100. This is the transfer function for a band pass filter with geometric center frequency 100 radians per second and bandwidth is 20 radians per second. Now we shall discuss the next topic, which is bilinear transformation. And frequency warping. Okay, so as we discussed, why are we using bilinear transformation? To convert from analog filter transfer function to digital filter transfer function, right? How do we do that? So it is nothing but, so let me, before that, so bilinear transformation is transformation method. It's a transformation method method to convert to transform analog filter transfer function h of s to digital filter transfer function h of z. Okay, so how do we convert it? How do we transform it? What we need is h of z. Okay, since it is in z domain, so we are in, since it is in z domain, so it is a digital, right? So we are in digital domain, right? Is equal to the given analog filter transfer function h of s. Here in this transfer function, wherever s is there, so I have to replace it by 2 by t into numerator is z minus 1 and denominator is z plus 1. Okay, so where capital T here is sampling period. Basically we are converting from S domain, analog domain, to Z domain, digital domain. Fine. So I'm not going in deep into this equation. How do we get this equation? But let me tell you what's happening in terms of S plane and Z plane. Okay. So what we have here is S plane. In S domain we have S plane, right? And this is j omega. This is sigma. This is S plane. And the digital plane is Z domain, Z plane. So we will be having a unit circle. This is unit circle. So 0, 0, right? This is imaginary part of Z. This is real part of Z. Okay. So this is Z plane. So analog, and this is digital. So in S plane, when do we say that the system is stable? If the poles are lying in left half of S plane, right? If all the poles are lying in left half of S plane, then we call it as that system is stable. Whereas in Z plane, when do we call the system is stable? When all the poles are lying inside the unit circle, right? So this is the stable region. And in Z plane, so inside the unit circle, this is the stable region. Okay, so whenever we are replacing h of s, where s with 2 by t into z minus 1 into z plus 1. So what exactly we are doing is we are doing three things here. We are doing three things. Okay, first thing is the left half of S plane is mapped onto the inside of the unit circle in Z plane. So the left half of S plane is mapped to inside the unit circle in the Z plane. Okay, this is the first thing we are doing. So left half of S plane, stable region, is mapped to inside the unit circle in the Z plane, which is also a stable region. This is the first thing we are doing. And second thing what we are doing is the right half of S plane is mapped onto the outside the unit circle. So this right half of S plane is mapped to outside the unit circle. Okay, this is unstable region, right? I cannot say unstable region, but the right half of S plane is mapped to outside the unit circle. That is the second thing we are doing. Okay, and the third thing we are doing is the positive j omega axis. The positive j omega axis is mapped to the positive half circle of the Z plane. So this axis, let me put it in a dotted line, is mapped to positive half circle in the Z plane, whereas negative j omega axis is mapped to negative half circle in the Z plane. Let me put it in a dashed line here. This is the third thing we are doing. Okay, so basically we are converting from S, we are taking the poles or the transfer function from S plane to Z plane. That's what we are doing in bilinear transformation. This is nothing but bilinear transformation. Okay. Now we shall take up a simple numerical example to convert an analog transfer function to digital transfer function using bilinear transformation. Okay, so example, so given an analog filter whose transfer function h of s is given by 10 divided by s plus 10. What I need to do is I need to convert it to digital filter transfer function, and also I need to get its difference equation. And I have to take sampling period is equal to 0.01. and what is this? This is capital T, right? Sampling period is capital T. So given a transfer function in S plane which is in analog form, I have to convert it to Z plane which is in digital form, and I have to take the sampling period as 0.01. So solution. So what is given? T is what? T is 0.01 second, right? And also they have given us analog filter transfer function h of s which is 10 divided by s plus 10. Fine. So what I need is h of z, right? What I need is h of z. How do I get h of z? It is nothing but h of s. In Laplace domain, wherever s is there, I have to replace it by 2 by t. Numerator is z plus 1 and denominator is numerator is z minus 1 and denominator is z plus 1. Right? And what is t? T I have to substitute by 0.01. Okay, so we will do that. We will substitute it and we will see what do we get. So h of z is equal to h of s at s is equal to 2 by t z minus 1 divided by z plus 1. So h of z is equal to, what is h of s? It is given, right, which is 10 divided by s plus 10 at s is equal to 2 by 0.01 z minus 1 divided by z plus 1. And what is this value? This is nothing but 200, right? 2 divided by 0.01 is 200. So I can write it as 10 divided by s plus 10 at s is equal to 200 into z minus 1 into z plus 1. So let me substitute it. So h of z is equal to what? 10 divided by 200 into z minus 1 divided by z plus 1 plus 10. Right? So this is equal to, if I multiply numerator and denominator by z plus 1 here to get the common denominator, what do I get? 10 times z plus 1 whole divided by denominator is 200z minus 200 z minus 200 plus 10z plus 10 right? So 200 times z plus 10 times z, which is 210 times z, and minus 200 plus 10 is minus 190. Okay, we will see that. So this is equal to 10 into z plus 1 whole divided by, this is 210 times z, and this is minus 190, and this is equal to 10z plus 10 divided by 210z minus 190. Now to make it to negative power z, what I'll do, I'll multiply both numerator and denominator by z power minus 1. So what do we get? 10 plus 10 into z power minus 1 whole divided by 210 minus 190 into z power minus 1. Okay, just to bring it into a standard form, I have to make this 1, right? That is what the standard form says. So what is h of z for IR filter? It is b0 plus b1 z power minus 1 plus this goes on whole divided by 1 plus a1 z power minus 1 plus a2 z power minus 2 and plus goes on, right? So this has to be 1. So in order to make this 1, in order to normalize it to 1, what I'll do is I'll multiply both numerator and denominator by 1 by 210 and denominator also 1 by 210. What do I get? 10 divided by 210 plus 10 divided by 210 into z power minus 1 whole divided by 210 divided by 210 minus 190 divided by 210 into z power minus 1. Okay, so let me write it here. So what do I get? H of z as h of z is equal to, so 10 divided by 210 is, so 10 divided by 210 is 0.047. We get 0.047 plus 10 divided by 210, which is same 0.047 into z power minus 1. This is the numerator. Divided by 210 divided by 210, it is 1 minus, so 190 divided by 210, it is 0.904 z power minus 1. Okay, so this is our digital transfer function h of z. Now I want to convert it to difference equation. I need this in terms of difference equation, right? So in order to get it to difference equation, what is h of z? It is 0.047 plus 0.047 z power minus 1 divided by 1 minus 0.904 z power minus 1. So what is h of z? H of z is what? Z transform of output divided by z transform of input, right? Y of z by x of z is equal to 0.047 plus 0.047 into z power minus 1 whole divided by 1 minus 0.904 z power minus 1. So I'll cross multiply this. What do I get? Y of z minus 0.904 z power minus 1 y of z when this goes to this side. I'll take this x of z to the other side is equal to 0.047 x of z plus 0.047 z power minus 1 x of z. Now I'll write it in terms of z transform of output, which is y of z is equal to, if I take it to the right hand side, so what do I get? 0.904 z power minus 1 y of z plus this term 0.047 x of z plus 0.047 z power minus 1 x of z. Now what I'll do? I'll take inverse z transform on both sides. So what do I get? What is the inverse z transform of y of z, which is y of n, which is equal to, so this is nothing but z power minus 1 y of z is what? It is shifted right one time now. So 0.904 y of n minus 1 plus, so this is 0.047 x of n plus, and this is 0.047 x of n minus 1. So this is the difference equation for a given transfer function h of z, something like this.